Good morning. My name is Enrico Garaldi. I'm currently a research fellow at the Max Planck Institute for Astrophysics in Munich. And it is a pleasure for me today to be here and to present you some of the first results from the Thesan simulation suite. This is a suite of simulations that have been developed and run on SuperMUC and G in the past couple of years by me and by my collaborators that are listed here in this slide. And as the title slide says already, the talk is going to be focusing on the formation of the first galaxies and on something called cosmic reionization, in particular, how these two research fields in astrophysics actually combine and get together in this numerical project. So I will spend the first few minutes just describing and introducing galaxy formation and cosmic reionization to you all. And then I will move on presenting you some of the first results and technical challenges that we had to face during the development of this project. So let me start with a biased history of the universe, biased in the sense that I will only touch upon a few key periods of time in the evolution of the universe that are relevant for the science addressed by the Thesan simulations. And during the course of this talk, I will use something called redshift, which is just a way to measure cosmic time. So the time since the Big Bang, that, as you probably all know, is the current leading explanation for how the universe started. And the redshift is just a way to encapsulate in a specific form the expansion of the universe that started right after the Big Bang and goes on even today. And the only thing you really need to know to understand the following is that a redshift of 0 corresponds to today, and a redshift greater than 0 corresponds to time closer and closer to the Big Bang. So let me start indeed with this Big Bang that we think was the beginning of our universe, where time and space and everything inside the universe actually came into being. And the Big Bang left behind a distribution of very hot and very dense gas that the expansion of the universe itself started to cool down until roughly 400,000 years after the Big Bang. This gas was cool enough to allow protons and electrons to recombine, forming hydrogen atoms, and at the same time leaving photons free to travel and reach us after a journey of 14 billion years. And this is something we can actually observe, and we have seen that this is something called the cosmic microwave background, or CMB, as shown in this picture by the Planck satellite. And the very fact that we observe this CMB not only tells us a lot of information about the content of the universe, but tells us that the universe was neutral at that time. What follows the recombination epoch is something called the Dark Ages, a period of time where there are no sources of light in the universe, but there is only a distribution of neutral gas that is collapsing under its own weight. And this gravitational collapse triggers the formation of the first stars and then the first galaxies in the universe, roughly 100 million years after the Big Bang. And these galaxies and stars started to pour a large amount of ionizing photons into their surrounding, reionizing the gas in the universe and driving a process that we call cosmic reionization. This lasted roughly 1 billion years, or down to redshift 6 or so. And by that time, all the gas in the universe outside of galaxies was completely reionized. What follows is then the remaining 90% or so of the history of the universe, where more and more stars and more galaxies formed and kept forming until today. So this period of first galaxy formation and cosmic reionization has been recently the target of a lot of interest. And to show this, I just want to show you some of the currently available or forthcoming instrument targeting as their science case the formation of the first galaxies or the properties of the universe during this cosmic reionization. And the reason why the formation of the first galaxies has become the new frontier in both the study of cosmic reionization and galaxy formation is that we can now actually observe and start to constrain with observation this period of time. And at the same time, cosmic reionization needs to understand galaxies because they are the sources of ionizing photons driving this process, and galaxy formation need to understand the first galaxies because they are the progenitors of today's object, including the Milky Way in which we live. But this convergence of these two fields also poses a very hard challenge. We need to simultaneously understand the properties of the gas in the universe, the so-called intergalactic medium between galaxies. We need to understand the properties of the first galaxies that emerge in our universe, as well as their connection, all in the same framework. And this is done at a time where only roughly the first 1% of cosmic stellar mass density was assembled. In order to tackle this challenge, we developed the Thesan simulation suite. While I'm going through a few details about the suite, let me just describe you what you are seeing on the right. This is a slice through the simulation at its ending times, or right after cosmic reionization. And you can see with different colors in the background, different physical properties of the gas, the density, the temperature, and so on. They are all written there. And the two circular inserts show you the forecasted view that the JWST Space Telescope that has to be launched in October, and the ALMA observatory in Chile would have of the galaxies in this simulation. At the same time, we are also showing you the flux distribution, flux intensity as a function of wavelength for the simulated galaxy. So while you look at this beautiful picture, let me just mention that the Thesan simulation are run using the repo moving mesh code that brings together the advantages of the mesh codes and the particle-based codes. It employs a state-of-the-art galaxy formation model, in particular the illustrious TNG one, that has proven to be extremely successful in reproducing a lot of different properties of low redshift galaxies, or galaxies today. We complemented this model with self-consistent radiation transport, which is a piece of physics needed to properly capture and explain the process of cosmic reionization. This is numerically solving the radiative transfer equation using a moment-based approach with an M1 closure relation. We also have a non-equilibrium thermochemistry in the simulation. And finally, we add dust creation and destruction process, because cosmic dust is one of the main channels we have to study these high redshift, very ancient objects. And all the results I'm going to show you in the remaining of this talk come from a set of papers that are in preparation and will hopefully be published very soon. So before moving to the results, really let me just mention that despite the incredible numerical effort required to reach a very high resolution in a large volume with this rich physical model, we also invested a lot of time in varying the physical model itself and studying the different possibilities allowed by our current knowledge of the high redshift universe. So in the following, I will just focus on the main fiducial model, the one underlined with the yellow line here. But this slide is just to show you that we have explored a rich variety of models, both in what concern the properties of radiation emitted by high redshift galaxies, as well as the properties of dark matter. So let me start with a movie. And this movie shows you at the top the density of dark matter, gas, and stars. And at the bottom, the ionized fraction, temperature, and photon density in the gas. And this is showing you the evolution through a slice in the simulation. And as you can see, as the first stars form and start to pour ionizing photons, the gas in the simulation gets more and more ionized until the entire simulation is completely ionized, and this marks the end of cosmic reionization. Now, let me just focus on a small portion of this simulation, just to show you that on top of these statistically significant large volume properties, we can also really see the details of individual galaxies. So what I'm going to show you next is just a movie zooming in one of these galaxies, and then showing you the gas density, and now transitioning to different physical properties. So we include in the simulation magnetic fields and their pressure support, dust, and you are seeing the dust to metal ratio. This is showing you now the temperature, and you can see this bubble due to feedback process from star, and now you have the H1 fraction. And now the movie will go back to density and keep zooming, showing you the amount of details we can reach. And just to give you an idea, we are now at a zoom factor of more than 400. And again, showing you that we can resolve individual feature and individual physical processes occurring at the center of individual galaxies during this time. Again, you are seeing now the dust temperature, the metallicity, so the amount of metals in the gas, and finally the H1 fraction. So let me move on to something more quantitative. The first plot I want to show you is the reionization history of the universe. what you are seeing here with white points is a collection of observations from the literature. Just to remind you, high redshift means closer to the Big Bang. So the right of this plot is closer to the Big Bang. The left-hand side of the plot is closer to today. And I ask you to focus on the red line, which shows you the main fiducial model from our simulation suite. And you can see that this line goes through most of the available data points, although the data are really scarce at this redshift because it's very difficult to observe such distant time in the past. This actually is the quantity that we use to calibrate the only free parameter at high redshift in our model, because all the other parameters were taken as they are from other simulation efforts. And this parameter is the stellar escape fraction, so the amount, or rather the fraction of photons escaping from stars that are put into the surrounding gas. And this is meant to represent the unresolved high-density cloud that indeed the simulation cannot resolve. And now we can move to some prediction or output from the simulation. This here is the UV luminosity function. So there are a number of galaxies as a function of their luminosity in the UV band of the spectrum. You see with different points, or rather with points, different observations from the literature. With different lines, you see prediction from the simulation suite, and different colors shows you a different redshift. And this is remarkable because usually the UV luminosity function is either an input to the simulation targeting this period of time in the history of the universe, or it is calibrated against to fix some of the physical parameters of the model. In our case, however, the UV luminosity function is not an input, but rather an output of the simulation. And as you can see, it predicts, it matches pretty well the observed data. The next plot I want to show is the distribution of temperature and densities in the gas in the simulation. During reionization, these are the top panels, and after reionization at the bottom. And on the left-hand side, you see the results from our main fiducial model. On the right-hand side, you see the results from a run that uses the same initial conditions, but now with the old TNG model. And as you can see, the crude approximation that the TNG employed for the gas that does not capture really the variety of gas conditions present in the universe at any given time, which are, however, captured by Thesan thanks to the inclusion of a self-consistent radiation transport solver. In the last few minutes, let me just mention a few of the technical challenges that we had to face during the development of these simulations. The first one is that the richness of physical processes included in this simulation entails that each resolution element has to be described by a lot of variables, each one of them storing a different physical quantity, which requires a lot of runtime memory. In particular, even after our efforts to move from a purely distributed memory approach to a hybrid approach where redundant data are stored only once per node at the price of a more complicated communication pattern, and even after an extensive analysis that identified and removed unnecessary double precision variable, moving to single precision, we still need just short of 100 terabyte of memory, of runtime memory for our main flagship simulation. But this effort nevertheless managed to reduce the memory required per resolution element from 12 kilobyte to 2.5 kilobyte, with a lot of benefits, both for this simulation and for future simulations. The second technical challenge I want to address is the code weak scaling. In fact, these simulations were among the first to push the code to such a large number of cores. We have, in particular, for the main run, we use approximately 60,000 cores. And these unveiled some suboptimal code scaling that we addressed, in particular, concerning the domain decomposition and the tree-based gravity. I should say, however, that these improvements were achieved in close collaboration with the Millennium TNG team. And you can see here on the left an example. So different line style shows you different parts of the code, but I asked you to focus on the solid lines that shows the total amount of time per time step in the code. And as you can see that with the old version of the code, the yellow line, where we had a suboptimal scaling, while the blue line showing the new code scaling is very close to optimal scaling. And since my time is up, I will just leave here my summary, and thank you.